Welcome grade 10s. Today's lesson we are going to be looking at functions, trigonometric functions specifically, and we're going to be dealing with three, namely your sine function, cosine and tangent. So let's have a look and see what our key focus is for today's lesson. As mentioned, we're going to be dealing with our graphs, functions. The two terms are interchangeable, and by this stage you should have already covered quite a few of your functions, namely your straight line or linear function, the quadratic function, which is also known as the parabola. So by now you should be very familiar with this terminology of function and be ready to move along to trig. With regards to each function, we are going to be looking at 5 properties. We're going to be looking at the shape of each of the functions, what are their intercepts, domain and range, and we will revise what that terminology means, and what are your minimum and maximum values, and as well as your period and amplitude. So there's quite a lot of terminology, and they are words that maybe you haven't come across before, words such as asymptotes, amplitude. If you struggle with the terminology as we work through the lesson, write the word down, highlight it, repeat it after I say it so that you become familiar with the way it's said, pronounced, and how it looks, so that you become familiar with the terminology. I know many of you do struggle with that, and it's okay. It's just a matter of working through it. And with regards to each function, we're also going to have a look at then the effects of the changing amplitude, and once we have these functions drawn, we're going to shift them up and down and from side to side. So we're going to have a look at that. All right. Before we move along, there's just a few things I want to discuss, and namely it's our notation. So we've written here y is equal to sine theta. Now, what you are going to be familiar with is the notation of f of x is equal to a sine x plus q. What do all of these mean? Namely, if you're using the notation of f of x, that means a function in respect to x. And the x value in this equation is representing our angle. So it's very important that whatever is in your brackets here is related to the angle. So if we wish to have this as sine theta, for example, what we have here, if we put it in f of notation, it would have been f of theta. Okay, so we would have written f of theta is equal to sine theta, for example. So those must correspond. So that's the first thing to bear in mind. Okay. Next, just to quickly revise, what does A tell us in this equation? Right now, the value of A, the standard value is 1. But the value of A can change, and we said that we're going to look at the effect of a changing amplitude, all right? And A is what affects that amplitude. So if A has a value of anything but 1, 1 is our standard, which we're going to work on intensely, but as soon as A changes to either a half or 1.5 or 2, 3, the amplitude changes. So that's the first transformation we're going to have a look at. And then lastly, we're going to look at Q. And Q has an effect on your graph, and we call it the vertical shift. So if this value here changes to plus 2, that means your graph is shifting up 2 places. So we're going to have a look at that in the course of this lesson, but the notation is very important. So again, without all my notations, we're going to put here that our standard we would write as f of x is equal, and I'm going to use one of the other functions, cosine of x, and that must be an x now. Okay, remember our a plus q, and this is what we call our standard function. For example, if I asked you what is the standard equation for the parabola, you would tell me f of x is equal to ax squared plus bx plus c, or ax squared plus bx plus q. Okay, so that's what we are referring to. Let's move along and begin. So we start off with our sine function, and like I mentioned, we're going to be dealing with 5 aspects and 5 properties, namely the shape, what are our intercepts, and our terminology of domain, range, maximum, minimum, and periods and amplitude. So we're going to start off, and I want you to cast your mind back to grade 8 when you were first introduced to the linear function, okay, the fancy way of saying a straight line graph. And when you first drew your straight line graph for the very first time, you didn't draw it using the dual intercept method or gradient intercept method. You most likely were given a table for your x values, and you substituted that into the equation that was given, which gave you your output value, which was the y, and then you went and plotted those coordinates, and you drew little dots on your Cartesian plane, and then you joined the dots and you got your straight line. Now, because we are starting trigonometric functions today for the first time, many of you may have done it already before, so it'll be a revision for you, but that's exactly how we're going to do this. We have got our standard equation of y is equal to a sine of the angle plus q, and we're going to substitute for the angle that we've been given and look at the y value. So let's have a look at that, and this table here is already filled in. Nice for us, okay, and we're going to start with our drawing if you have a look here. So our equation is our standard y is equal to sine theta, okay, and for sine theta we place those values in. So for example, sine of 0 degrees is 0. For some of you may be wondering, how did we get those values? And if you were faced with one of these tables that were empty along here, how would you find all these values? Okay? And how do we get these values? Okay? Well, those can be chosen. Here we've decided to go up in intervals of 30. You would notice we start with 0, 30, 60, 90, 120, all the way up to 360, okay? And let's have a look. We're going to bring up our calculator here to have a look. And this over here is my equation, sine theta. Theta, we're going to substitute with 0, okay? So into the calculator we put sine of 0 degrees equals 0. Okay, and that's why we have that there. The next one is sine 30 degrees. So let's try that now. Sine 30 degrees equals 0, 5. And so on. And that is how we have filled that table. Okay, so sine of 60 degrees, 0,866. We rounded off to 2 decimal places to get 0,87. All right, so now let's get to the exciting part where we actually go and plot this. We now simply need to label our Cartesian plane, so label our axes, and this is always a nice and good habit to have. Now remember, x, right, is our angle, which means these values here of 0, 30, 60, 90, 120, etc. are going to be plotted on the x-axis because that is our angle. Remember, just as we can write y is equal to sine theta, we can also write y is equal to sine x. Okay, so those are our angles. And I'm going to plot here 90 and 180 and 270 and 360. Okay, so those are my points over there. Then we have a look at the top. Okay, which, the bottom, sorry, which is my value. Now remember here for sine theta, of where theta is equal to 0, we got a value of 0. This sine theta, according to our equation, is equal to y. So that means these values are going to be found on your y-axis. And I'm going to use an interval of a half here. 1, 1.5, and 2. So there are several of these points that we are not going to plot exactly because we would have 0 and we would have 30 over here and 60 over here, and we can try and plot those. But for now, we're just going to plot those. So sine theta of 90, so sine of 90 degrees is 1. So that means I would start over there. Okay, of course, my origin, sine of 0 degrees is 0. And then we move along to 180 and 180 and 0. Now, I hope you're following and noticing that I am putting these as coordinate pairs. Okay, this is simply plotting. Okay, this is on my x-axis, my y-axis. And then looking at 270, it's 270 and minus 1. That means we are over here. All right. And lastly, sine of 360 degrees is 0, and we are over there. Okay, and many of you are looking, going, well, there's dots everywhere. How am I going to join this? And we're going to join it with a gradual line, and you would need to do this freehand, because if you use your ruler, you're going to get straight lines, and we need a smooth shape. Okay, so we're starting to look at our first property. What is our shape of our sine graph? And we look at that. I'm just going to edit slightly over here because I'm not too happy with that. Okay, I wanted to go through that point there. Okay, right, and that gives us our shape. That is the shape for the sine graph. We're going to have a look at more details there. But if you have a look, if I were to go and continue plotting, if I wanted to start with 30, we know that 30 degrees, okay, is probably found about here, and of sine 30 degrees, it gives me a value of a half, which is over there. And can you see that it lies on my graph? Sine of 60 is going to be closer to about here, and that's 0.87, and that would be somewhere along those lines there. So if you go and plot these, all those points are going to lie on that. So number one, we've dealt with shape. Okay, and this is our standard shape for a domain of 0 to 360, and we will discuss domain in more detail shortly. So this is our first one. So so far we've dealt with what is our shape. Now often you are going to be asked to sketch a sine function. Okay, can be your standard. And what we do is you are going to become very familiar with the intercepts. Now, what does the word intercept mean? So if you struggle with the terminology and the language, write the word intercept down now so that you know. Remember, intercept means, okay, if we're talking about our x-intercept, it's where the graph cuts the x-axis. And your y-intercept is where the graph cuts the y-axis. So to help you, okay, with the language, write the word intercept and maybe draw a little scissors so it reminds you that the intercept, x-intercept where the graph cuts the x-axis, y-intercept where the graph cuts the y-axis. So now let's have a look at these properties. What are our intercepts of our sine graph? And the most important ones, we've got lots over here, and it's the ones in orange that I've highlighted that we need to remember. So we start at our origin, and our first coordinate is 0 and 0, okay? So if we have a look there, this is cutting our x and y intercept. Here is another intercept. This happens to be a x-intercept, okay? And our x is 180 degrees. Remember, these are degrees. That's just the value. So 180 and 0 again, all right? Remember, x-intercept, your y value is always 0. And the last x-intercept is 360 degrees and 0. So these over here are our x-intercepts. And reminder that x here is our angle. Our y-intercept is going to be our origin as well. And you will notice that along this y-axis, it does not cut the y-axis again. Okay, so far you're happy with those. Other important points are always, I just was in the habit, I just also learned the 90 and 270, which gives me those 2 points. Okay, and we are going to discuss those when we discuss amplitude and maximum and minimum values, all right? But I always like to remember that my 90 degrees gives me a value of 1, and that 270 degrees is negative 1. And I just like to remember that that is important. Okay, and that means we've now discussed our intercepts. Domain and range. What is domain and range? Okay, and many of you are able to say domain and range are the x and y values. And then often we tend to forget which one is which. Sometimes in the test you think, oh, okay, so I know domain and range are my x and y values, but is domain the y values or is domain the x values? And we can't remember. And I've got a funny little way to remember it that I was introduced to by one of my very interesting students. And they told me range you are going to remember are your y values, because y has got the tail like the G in range. And I giggled at the first time this learner told me this, but it has helped many learners after that since I've told them that. And in fact, it sometimes even helps me when I get into a state of confusion. So that's something little to help you remember if you struggle to remember those. So your domain are all your x values, and your range is your y value. So for example, if I asked you, what is the domain of this function? So you're sitting there going, all right, domain are my x values. But how does that help us? These are our x values here. So the way in which you would write your domain for this particular function, we start at 0 and it is included. I'm going to do this in interval notation. So I'd start with my squared bracket. Okay, and my x values continue all the way to 360, and that's where it ends. And 360 is included, so I could write 360 degrees. Does your domain have to be written in interval notation? No. You can also use your inequalities, or you can do it as set builder notation. It's whichever notation you feel more comfortable with. In terms of inequalities, the way in which we would write this is x is greater or equal to 0, but less than or equal to 360. And these two mean exactly the same, it's just written in a different way. Okay, so you would do it in whichever way you're more comfortable with, unless the question says give your domain in interval notation. Then you must follow the instruction from the question. All right. Range are our y values. So let's have a look at our y values. Now that means they want all the y values. So all these values from there, because that's our biggest y value that we've got. If you notice, this function does not go over there. So it's all these values all along here. And I can see that it went all the way through to -1. So this over here is what my range is. Fabulous. How do we write that mathematically? Okay, and that's where sometimes the trick comes in, that you know what the question is asking, but now how do we write it? And again, it's the same thing. You either write it in interval notation or in set builder, whichever you are more comfortable with. So let's do that now. So our range would be, it includes the -1, it includes the +1, so we use square brackets for both, or we would write y must be greater or equal to -1, but less than or equal to +1. And that is the way in which we write the domain and range, and we will have more practice with this when we deal with questions. Now, maximum and minimum values. Think back to when you have dealt with the parabola and they ask you for your maximum or minimum value. Okay, now when they discuss that, we're always talking, they ask you for your maximum or minimum value. That is referring to the y coordinate of your turning point. Okay, can any of you remember what the x value of the turning point is referred to? So now we're doing a little bit of revision. So we've got x and y, and we say that this coordinate is representing our turning point. The special name that we give the x value of the turning point is called the axis of symmetry. Okay? And the special name that we give our y value of a turning point is called the maximum or the minimum. Not maximum and minimum. It can't be both. It has to be one or the other. So just to quickly, if you've got a sad face, okay, that means your turning point is going to be somewhere along there. And that means you would have a maximum value because that's the highest value that your y can have. If it's a minimum, you're going to have a happy parabola, okay, and your turning point would be down there, and that's minimum because that's the lowest value. Now, when we refer to maximum and minimum values with our trigonometric functions, we are also looking at the turning point, so specifically this point over here and that point over there. Okay, so that would mean that your maximum value for your sine function is going to be this one over here. What is the value of x at this point? 90 and 1. So we've summarized the 5 properties that we have a look at our sine function. However, there's just a few things that I want to add just so that you can see what they are on the actual graph. So this point over here, remember this is a half, so this over here would be negative a half, and this point over here would be my -1. Okay, which is the opposite here. This would be -1.5, -2, etc. Now, let's have a look at this point over here, and this one, and these ones over here. Okay, these points are what we were talking about with regards to maximum and minimum. Okay, if we have a look here, this is our maximum value where x is 90 and y is 1. So this is your maximum point. Here we have a minimum because our y value is -1. So our coordinate, however, would be 270, -1. Remember though that I said when you're referring to minimum and maximum, we are talking about the y coordinate. In a similar way, when we look at the negative side of the x-axis, we will see that over here we also have a minimum point. But here our coordinates are -90 -1. So we have a minimum at -1 as well. And here we have our maximum value, and these coordinates are -270 and +1. So these over here, that's what your maximum and minimum look like on the actual graph. Now, period, looking at the English language, period is, if I can say to you, what period of time do you spend on your homework? Okay, or what is the duration of your homework in the afternoon? So it's referring to a time. Now, when we look at the period of a sine function, we are asking ourselves, from what point to what point does it take for this function to complete one full cycle. Now what we have here from beginning to end is one full cycle, and it goes to 360. Now you'll notice that I've got this part of the Cartesian plane that I haven't used yet, and some of you may be going, okay, well, so why is it there? Because this graph continues along the side, where here you will have negative 90, negative 180, negative 270, and negative 360, okay? And what happens is this graph is then reflected. So here where you've got 90 and 1, here you're going to have minus 90, minus 180 and 0, negative 270, positive 1. So it's the opposite values. And what happens is you get this, okay? And this is now your full cycle. So what we say is the period, okay? The period of your sine function is 360 degrees. Let's have a look at the word amplitude. So having a look at amplitude, here, the amplitude is your height. So because from the origin, and I like to work from the origin up to the maximum point, that height over there is 1. So that means that the amplitude of this function has a value of 1. Get my pen back. Okay. So now we've discussed all 5 properties of the sine function, and before we move along to cos, I'm just going to revise. I'm doing this in great detail because now when we do the cosine function, we're going to go and do the same 5 properties, and we'll be able to do it a lot quicker. So let's have a look. Our shape, we've seen that the shape of our graph gives us a shape that looks a little bit like that, okay? Intercept, we know that our x-intercepts lie on the origin, 0, 90, and 360. Those are our x-intercepts. That's where the function cuts the y-axis. So it is at 0 degrees, 180 degrees, apologies, I did say 90, so that is incorrect, it's 180. Even as teachers make mistakes. 180 degrees and then 360. So those are the 3 key points where the graph cuts the x-axis. Domain and range. Domain are our x values, range are our y values. Minimum and maximum values, you're looking at the x and y coordinates of the 2 turning points, which are at 90 degrees and at 270 degrees. Okay, and then we've looked at what the word period means and amplitude. This has been a lot of information that we've just revised and worked through. So this is going to take us to a short ad break. Gives you the opportunity to get up and get something to drink, let the blood flow. And when we come back, we're now going to continue with our sine function, but have a look at what happens when we want to change the amplitude and when we are going to vertically shift the graph up and down. So we're going to look at the transformations now. Okay, but that's when we come back from the ad break, once you are a little bit more revitalized. So see you shortly. Welcome back, and we are going to continue with our sine function. Before we move along, I have a question for you. What is the standard equation for your sine function? Okay, and I hope you've all said f of x, or you could have y, depends on the notation you're using, but let's get used to using f of x. F of x is equal to a sine x, and I'm going to erase that because that looks like a very strange sine x plus q. So that is our standard equation for a sine function, and we've had a look at what the shape of this function, we've looked at the properties, and now we're going to have a look at the effects. that changing the amplitude does to the sine. So first of all, the effect of the amplitude on this equation, which variable affects the amplitude? And if you've said A, you are quite correct. So this is what affects your amplitude. So for example, if I were to give you an equation which was f of x is equal to 3 sine x, and we are going to assume that q for now is plus 0 because q has a different effect that we're not going to deal with just yet. Now, I'm not going to draw an entire, put it on a grid, but just to get a basic idea. Okay. Now, we've learned before we went to the ad break that our sine function has a shape of that, and just want to extend this line, well, moving him, but that's okay, that's almost the same thing. Okay, now this was the function that we've learned, where this point over here was 0 and 0. This one, can you remember what that was? Our maximum and minimum value, remember, it had 90 degrees and 1. This over here was one of our x-intercepts, which was 180 and 0. This was our other one, which was 270 degrees and minus 1. Writing this all the way too close together. Okay, 270 degrees and minus 1. And our other point, which was our other x-intercept, which was 360 degrees and 0. And that was our standard sine. Now, what happens when I give you a function that looks like this? F of x is equal to 3 sine x, where the a value is not 1. Because remember, a is your amplitude, and the amplitude of this graph was 1. What happens now when this amplitude is 3? Now, this is not complicated at all. And just to make it easier for you, if we have a look at the coordinates and we write them down here, it's 0 and 0, 90 and 1, 180 and 0, 270 degrees and minus 1, and 360 and 0. So here are all our coordinates that give us this. Now, if you have a look, where this over here was my amplitude, okay? So if we want this amplitude now to be moved to 3, what do you think happens? That means this value is going to become 3, okay? So how do we now look at this and make sense of it so that we know how to draw this? Well, simply what that means is this value over here and this value is now going to become 3. It's the only two values. These are still your x-intercepts, okay? And it does not change. So A has an effect on the amplitude, okay, but it does not have an effect on the x-intercepts. It does not have an effect on the period either, okay? And that means what your graph is going to now look like will look something along these lines, and I want my color. So now I'm going to draw this one over here, and it is going to look something like this. Okay, so it looks a little bit more hyperactive because this is going to now 0.3. So this still remains 0 and 0. Okay, so can you see that your x-intercepts remain unchanged? Okay, unchanged. This now becomes 90 degrees and 3. Stays the same. This one now would be 270 and minus 3. Now, this isn't done in a very nice, tidy way because I'm just sketching to show you. But what I'm going to do now is let's have a look over here at our sine function that has been drawn for us. Okay, now over here, this is our point clearly here would be our point where it would be 90 and 1. This is our next intercept, 180 and 0. This would be 270 and minus 1, and our last intercept, 360. Now you see it continues, and that is yes, because it's a cycle. Your sine continues, okay, but it takes a period of 360 for one full cycle to complete. Remember, a cycle, word cycle means there is no end and there is no beginning, so it just continues. But when we look at the domain, we look at a specific portion of the function. Now let's have a look at, we are looking at the values of a, which have an effect on the amplitude. So let's have a look at this function here, which is h of x is equal to 1.5 sine x. So we can see that this is going to have an effect because there is a value of a. Now have a look at that, 1.5. Can you see again your x-intercepts remain unchanged and only the height of the function has moved. So I almost say that it becomes a little bit more hyperactive. Can you see that it's going a little higher? Let's have a look at q of x, which is equal to 2 sine x. Now can you see that your height is going up to 2? And is even higher and comes lower there. And the blue, remember, is our standard. And for example, the example I gave you before, which was f of x is equal to 3 sine x, if we were to go and draw it, it would be somewhere up here because this is 2, the next one's 2.5, and then it would be 3. So it would be right up at the top. Okay, so I hope this gives you a nice visual of how this actually, how A affects your amplitude. So back to our slide. All right, effects of changing the amplitude. Let's move along to our next transformation, which is the effect of vertical shifts on a sine function. And again, we always start with our standard equation, which is y. Now I'll use y is equal to a sine x plus q, and we can interchange y and f of x, and that's why I'm doing that so that you're aware. We've discussed that this has an effect on our amplitude. Now what about vertical shifts? That means we're looking at our q value. If we are adding q, it means our function is shifting up by that amount, and if we are subtracting q, it means our function is moving down. Okay, and when I say shift, if we think about the function we've just worked with now to look at the effect of the amplitude, the actual graph did not move. We didn't lift the sine function up and move it somewhere else. Okay, all that happened was that the height became higher. Okay, and the amplitude changes. One thing I didn't mention, and I'd like to mention it now, is when you change your amplitude, it didn't affect our x-intercepts, it didn't affect our period, it didn't affect the domain, but it does affect your range, your y values, because now your y is going higher. So amplitude affects range. Just bear that in mind, and we're going to look at that when we do the examples. Now we're looking at our vertical shift. This is where you actually physically shifting. So shifting is moving. We move the graph. It's almost like we're picking it up and putting it somewhere else on the Cartesian plane. But we can't just do that. We have to follow the instructions. And let's have a look at ours over here. We're going to remove these and go back to our standard. Now, if I were to now put sine x plus 1, what do you think that's going to look like? What do you think that black function is going to look like on this? And I want you to try and think, what do you think it's going to do? Remember I said that your q value, so having a look at f of x is equal to sine x plus 1. Clearly this is our q value plus 1. We said if we're adding, we're moving or shifting the function up by that amount of units. So is this what you were expecting? Okay, so can you see here that all your coordinates are affected, because this is now no longer 0 and 0. This now, the new coordinate of the function is 0 and 1. Here we had 90 and 1, which was our original. This is now 90 and 2. So can you see how that is shifted up? That means, okay, for our standard coordinates, which are 0 and 0, 90 and 1, 180 and 0, 270 and -1, and 360 and 0. So having a look at this, can we see that our x values have remained the same? X values are not affected. What is affected is that our y value. So that means, okay, we need to add 1 to every y value. So to get our new function, if we wanted to now go and plot this, if we were given f of x is equal to sine x plus 1, that means we now need to go and add 1 to all my y values. So my new coordinate here would be 0 and 1, 90 and 2, 180 and 1, 270 and 0, because minus 1 plus 1, and 360 and 1. And that's exactly what we have over here. Let's have a look where we subtract. H of x is equal to sine x minus a half. So here, can you see that we've now subtracted a half from all our y values, and this graph has shifted, so we've almost picked up our blue graph. The shape remains the same, and we've now moved it half units down because it was subtracting. So let's have a look at our properties. Has this affected our shape? No. Has this affected my intercepts? Yes, because here my intercept was at 0 and 0. Now it's 0 and half. So it has an effect on our intercept. And here, can you see how the intercept has shifted? So it has an effect on our intercept. Does it have an effect on our maximum and minimum values? Yes, because they are now different. Does this have an effect on our domain, our x values? No, because our domain are the x values, so no effect on domain. Has it had an effect on the range? Yes. Okay. Has there been an effect on the amplitude? Now this is a tricky one. Is there an effect on your amplitude? No, because here, being our standard cos, our standard sine function, apologies, our height was 1. But if you have a look now where this is shifted to a half, has my height changed? No, because we're going from negative a half to positive a half. And what is that height? It is a height of 1. Okay. Same over here. If we have a look, has my height changed? No, because my function is starting here at 1, all right? And I'm going to 2. 2 minus 1, still 1. So amplitude is not affected. Okay, so now let's put this into practice and move along to an example to see how this works. And we've been asked to sketch a graph of f of theta is equal to 2 sine theta plus 3. Okay, and here we are going to see how we actually apply a domain. And it says here for theta, okay, which is an element of 0 to 360 degrees. That means we must only draw this function for this domain. Okay, so let's begin. I'm going to begin by labeling my Cartesian plane and my axis. And this is, of course, going to be my 0 value. This is 90, 180, 270 degrees, and 360. Now you'll notice that I have left grids in between, so that means I'm actually going up in intervals of 45. Hope you notice that, okay? And I am going to start. Now I always like to start and draw my standard, okay, so that I know how the effects of amplitude and the shift are affecting my graph. So that's a habit that my teacher got me into, and it's worked with me. If you don't like to go and do that extra bit, then don't do it. It's not a problem, but it's nice and quick. So we know we're going through these points over here. no, that's going to be minus 1 there. So let's just undo that quickly. So we're over there and there. So my original would look like that. Do I put arrows on the end? No, even though this does mean it continues, but this is the domain they've given us, so they only want us to draw from 0 to 360. Okay, now I'm going to change my color to pink, and I'm now going to start working with this information because there is a 2 before, so I know this is affecting my amplitude. This 3 is added, so I know because it's been added, my graph is actually shifting up. So let's have a look at my effects. And I always start having a look at my original coordinates. Now, if we have 2, that means we're changing our heights. And remember, that only affects then this coordinate and this one, our maximum and minimum values. So my origin remains at 0 and 0. Okay, 90 is now not 90 and 1, but 90 and 2. So there's my first change. Next is 180 and 0. That remains unchanged. 270, and this now is going to become minus 2. So I've considered that. 360 degrees and 0. Okay, so that means now I have considered my A value and I've looked at how that affects my values, my coordinates. Now, this addition of the 3 plus 3, that's my Q value. Remember we said that's the vertical shift. This means that I'm actually going to take this graph that I've got and I'm going to shift it up. By how many? 3. So that means we need to add 3 to all of these. Okay, all my Y values. That means my first one is going to be 0 and 3. So, and what I'm going to do now, I'm going to erase this. Okay, because I'm going to run out of space with my 3, so let's have a look here now. I'm going to make this 1, 2, and this is going to be 3. Okay, and I'm going to continue with this as 0, and let's rather use the pink. I think it's easier for you to see at home. So 0, 90, 180. And it's very important that you see these steps because this is the kind of thinking process that you've got to go through at school, because they will often also only give you the grid and you need to add in the other information. So now let's begin. We know we need to add 3 to this, so now it's going to be 0 and 3, which gives me a point there. 90 and 2 plus 3 is going to give me 5. So if this is at point 3, this is going to be 4 and 5, so it would be somewhere up there. 180, and that's going to give me 3 again. 270 degrees minus 2. Now minus 2 plus 3 is going to put me at point 1 over there. And then 360 and 0, adding 3 to that is going to give me 360 and 3. And there we have our function. And I want to be a little bit pedantic because now, even if you do this, always go and rub that out, because remember, the question said from 0 to 360, and if I go past that, that's already moving on to negative 0,03 or along those lines. So I go and erase that just to make sure that I have stuck to what the question has asked me. And there we have our function. We then label it, and it was f of theta, so I now go write that f of theta, and that is what f of theta is equal to 2 sine theta plus 3 looks like. So by doing this example where we've dealt with changing the amplitude and doing a vertical shift and looking at the domain, I hope you've been able to look at this question in a different light and being able to apply that knowledge. Okay, all right. Let's move along to our next function, which is our cosine function. And again, we look at the same properties. and we've got our table here. And just as we looked at key areas, we are now only going to look at 0, 90, 180, 270, and 360. So there are values in between. Now, how are we going to get those values? Because now this table is not miraculously filled out like the one in the sine function example we did. And I hope you're sitting at home or wherever it is that you are, and I hope you've already got your calculator in hand and busy filling that out. So let's do that together now so that you can see exactly how we do this. So let's fill these values in. And we start with putting in cos of 0. Now, remember 0 degrees is one of your special angles, and you should have expected an answer of 1. This has been dealt with. Okay, so we know that that's a value of 1. And cos 90, also another special angle, so you should know this answer as well. You should know that that is a value of 0. So let's fill that in the meantime. Okay, so we know that that's a value of 1. This is a value of 0. And let's see what cos of 180 degrees is equal to, -1. Okay, and then lastly, cosine of 360 degrees. What does that give us? And it gives us a value of 1. So let's fill that in and go and draw this graph so that we can see what our standard looks like. So this we know is -1, and we know this is 1. And I forgot to have a look at 270. So let's do that together. Cos of 270. Make sure that you have gotten the same values at home, which gives us a value of 0. Okay, so we're going to go in intervals of half. So this would be half, and this would be 1. So here is where I find 0 and 1. Next is 90 and 0, which we have over there. 180 and -1. So this would be -half, -1. And 270 degrees and 0, and 360 and 1. And this is what our cosine function looks like. And some of you may be going, oh, that looks like a parabola. Careful, because with our negative, okay, remember our negative is a reflection, so we would have the points here and here and here and here. So you actually again have this function that looks like this, okay, it's rounded. So there is that cycle, and just so that you know not only to consider that part. Okay, so that is what your cosine function looks like. And because we've worked here with an interval, it is a little more squished. If I had to have stretched these intervals out and gone in intervals of 30s, the graph would become wide and you get a more gradual curve. Okay, so this is now our function cosine, all right, which is f of x is equal to a cos of x plus q. And the function that I have just drawn over here, this part here, would be f of x is equal to cos x on its own. You would notice that this does not mean that my value of a is 0. No. Because then 0 times cosine of anything would be 0. Remember, when there's nothing there, we know it's our ghost 1. So the value of a is 1, which means my amplitude is 1. There is no plus or minus anything, so we know this would be plus 0, which means my q value is 0, so there's no shift, and hence that's my standard cos. Now let's have a look. We've dealt with our shape. Our intercepts, okay, our x-intercepts lie at 90 and 180. Unlike our sine function, the sine function had 3 intercepts, okay? Here we've only got 2, our x-intercepts. But have a look. This now, our y-intercept is not at the origin, and instead is at 0 and 1. So these are some of the differences we need to have a look at. What about our domain? Remember, our domain are our x values. So we would say x is an element, and we're looking at, these are our x values. So again, 0 is included all the way to 360. So that is how I would write my domain, and again, you could do that as inequalities. What about our range? Our range here would be an element of, and can you notice it's going up to 1 to negative 1. So our range is the same, 1 and negative 1. So can you see now that we've done it for one function, it becomes so much easier to do it for the others. And having a look at our maximum and minimum values, this over here would be one of them, and that because they are your turning points. Okay, and that's why it's important that I drew the negative part on the x-axis of this total cycle, because otherwise that over there would not look like a turning point to you. Okay, so those are those values. What about period and amplitude? Now, your period of a cos graph remains 360 degrees as well. Okay, so that means it takes 360 degrees to complete a full cycle of your cosine function. Alrighty. Now, what about amplitude? Again, amplitude is that value from 0 to where. So because this is from 0 to 1, that means this function has got an amplitude of 1. So I hope you're now starting to see that at first when we dealt with this in the sine function, it seemed to be a little bit complex, lots of information, but now that we've practiced it, applied it to questions, and now it's the same with the cosine with some differences which we've highlighted, I hope you're finding it a lot easier. So let's have a look and see what the cosine function looks like if there is a change in the amplitude. So an example could be y is equal to 2 cos x. Now remember, amplitude is that height. It doesn't affect your x values, and it doesn't affect the intercepts. So a change in amplitude, it's almost like if the value is becoming bigger, it's almost like you are stretching this graph. Okay, and if the value becomes smaller, it's almost like it's becoming wider, but there is no physical movement on the Cartesian plane. So consider this function, and what do you think it looks like? All right, let's have a look at our standard. Okay, so can you see here, this would be 0 and 1. We've drawn this part here. Okay, all right, so it's got this lovely curve. That's what we had. That's from 0 to 360. Now, the example I've just given you is f of x is equal to 2 cos x. I think that was the example we had a look at, so let's have a look. 2 cos x. So let's see if we've got this over here. Let's have a look at all the different changes. So here, t of x is equal to 2 cos x. Notice that your points remain exactly the same. Okay, what has happened? This graph has been stretched. So we are considering this point over here. Okay. That's what we had drawn. Now have a look at that. Can you see how we've taken the exact same graph and almost stretched it? What about if we choose a lower value than 1? Because we had 1 for our amplitude. Let's have a look at what happens to 1.5 cos. Where are you expecting this? Are you expecting now the graph to begin here and be wider, or what are you expecting? Think about that before I give you the answer. There we go. And we're looking at that. So can you see that now it's in between those? Okay. All right. And that is our effective amplitude. Let's move along and see what happens when we deal with our Q value. All right. So now vertical shifts in a similar manner. We've got y is equal to cos x minus 3. Okay, and just as we worked with q in our sine function, this, because it's a negative 3, means your function is going to move down 3 units, because this is my value of q. and that's your vertical shift. So let's have a look at what this looks like. So here we have our standard cos x, okay? P of x is equal to cos x, and that's what we've got here. Having a look, let's add a half. So remember, we're adding. So you should be expecting when this yellow graph comes up that this graph has physically moved up half unit. So let's have a look and see what that looks like. So can you see that here my x and y values have changed because I've physically moved it? Okay. Let's have a look at if I subtract that. Okay, and there you go. You have this where it has now moved down. Okay, and that is the effect. So now let's go and use this knowledge to answer our next question and do our next example. So it asks us to sketch the graphs of f of theta is equal to 2 cos theta plus 3. Again, my domain is from 0 to 360 degrees. So I'm going to start off, and remember, I am going to start off by putting in the points that we've got. So we know that our first point for cos is 0 and 1. Then we've got 90 degrees, then it's 180, then it's 270, and 360. Okay, and just to remind you of this, we're going to go back to our original slide. So remember, we have 0 and 1, 90 and 0, 180 minus 1. Okay, so that's just to remind you of where I'm getting those values. Okay, and that is minus 1, 0, and 1 again. Okay, so those are our original coordinates for cos. Now, if we have a look, we're going to deal with our first change. Okay, we know that is going to have an effect on our amplitude. Going back again to our original, okay, we know that this over here, our amplitude, would be affected at this point and that one, and of course this value there. So that means it's having an effect at 1, minus 1, and 1. So that helps us out quite a lot. That means we now know that this is actually going to be 0 and 2. This remains 90 and 0, 180 and minus 2, 270 and 0, and this is going to be 360 and 2. Okay, so now we've dealt with our effect of the amplitude on our standard. Now we must add 3. So that means we're going to add 3 to all our y values. And that is what we are going to plot. So let's begin. 2 plus 3 is going to give us 5. So we're going to make this 1, 2, 3, 4, and our 5 would lie here. So 0 and 5 means my function would be commencing there. 90 and 3, and we're going to make this 90, 180, 270, and 360. So going up in intervals of 45. 90 and 3 would place me here. 180 and negative 2, adding that's going to leave me at 1. So my function is there. 270 and 0, adding 3 to that is going to put me over there. And then lastly, we get 360 and 5 again. And I'm going to have this lovely function that looks like this. Okay, and there we go. Just like that, we now have f of theta. And we finish off by labeling. So we would say f of theta is equal to 2 cos theta plus 3. And it's as easy as that. So if you follow the steps, in other words, if you know what that standard function looks like, it is no problem if you also know what the effects of A and Q are. So that takes us up now to another commercial break to kind of get the blood flowing again, and we are then moving on to our next and last trig function, being the tangent function, and we again are going to do exactly the same thing and do a few mixed examples to wrap things up. So see you shortly. Well, Welcome back. I hope you are still high on enthusiasm so that we can get through our last trigonometric function, being the tangent function. And we look at the same properties of shape, the intercepts, domain and range, minimum and maximum values, period and amplitude. And there is another concept that we need to consider with our tangent function being the asymptote. And that will lead us to, now if we have a look at our table. So again, we're looking at 0, 90, 180, 270, and 360. And I hope you've already got your calculators out and that you've already found those answers. So tan of 0 degrees gives us a value of 0. Okay, and we can fill that out. 0. Tan of 90 degrees. Oh dear, you've got a math error. What now? Have you made a mistake? In fact, you have not, all right? And what this means is at this point, of tan 90, this is undefined, okay? The reason being, okay, we've covered it with our special angles. Remember, you look at your tan, we know it's till old age, and if you look, or tan your exterior, and if you look at when your radius has moved up to an angle of 90 degrees, your y and your x value, your x is at 0, and we cannot say y over x, it's undefined. So I hope you remember that from your special angle. So that's undefined. And that leads me to the concept of an asymptote. So this is another word, okay, that you're going to need to learn, know how to pronounce and how to spell and work through. Now, asymptote is an imaginary line where your function actually approaches it but never cuts it. So the easiest way to explain that is if you stand up now wherever you are and face a wall and stand 2 meters away from that wall and halve your distance, you are going to now be 1 meter away from the wall. Now halve your distance again, and now you're going to be half a meter away from the wall, and halve your distance again and again and again. Physically, you are going to hit that wall. Theoretically, you are just going to get closer and closer and closer, because then you'll get to a point where you are 0,0000 away from the wall. All right? And that is the asymptote. We approach that line, but never touch it or cross it. And that's the asymptote. So what we do with this asymptote is we generally draw a dotted line along that vertical line, showing and reminding us that the function can only approach it but cannot cross or cut it. Okay, or touch it. So we're going to have a look at that. Let's do a tan of 180 degrees. So clear that. Tan 180 degrees, and that gives us a value of 0. So we can now fill that in. 270 degrees, let's see what that does. So tan of 270 degrees, and again, math error. All right, so that means, again, that we have undefined. So what this means is, at this point, again, we have another asymptote. And we just need to now finish up by doing our last one. And this is probably my favorite trig function because it's a little bit more interesting. It's got a little bit more of a spicy shape to it than our sine and cos, and we get a value of 0. Okay, so hopefully you were able to do that on your own, and again I wanted to do it together just to show you how to deal with these two. Alright, so let's start drawing this. And immediately we're going to have a look, and I always like to start with my asymptotes, my 90 and 270. And that means along here, in fact, let's use this. So along here, in fact, let's use the dashed line. We've got that one there. Fabulous. So along here, this is going to be my 90. Okay, and that means that this is now my asymptote. Okay, this is now the asymptote showing at 90. And we need another one of those at 270. So 90, 180, 270. So this is now my asymptote. Great. So we've got that information in so far. Now it's a matter of plotting. So at 0, we've got 0 and 0. Then we know that's undefined. Then we have 180 degrees and 0, which puts us over here. Okay, 270 is undefined, and now 360 gives us that. I hope now you're looking at this and going, well, I have a problem. If you're working ahead of me, you're looking and going, I have a problem because I've got 3 dots. I have no other coordinate points to join. I cannot join these 3, and if you did, remember I said you cannot cross your asymptote. So what now? Do we give up? No. Let's use our table of values to get this information. So, and we've got the calculator to help us. So let's have a look at what tan of 30 degrees gives us. And we get a value of 0,577. So 0,56, which would then round off to 0,6. So we can put that in, and this is now 0,6. And let's have a look at what tan of 60 degrees is. Tan of 60 degrees, and that gives us a value of 1,732. Okay, and right, so now we've got something to work with. Now, if we're working and looking at 90, 180, we know that halfway through this point would be 45. So I know that 30 is lying to this side, and we would have 60 along this side here. Now it makes it incredibly difficult because we're not on grid paper here, and when you are asked to draw a tan function, the question would be sketch the tan function. You would have grid paper where you can mark and draw it accurately. So what I'm going to do is, on this table it doesn't have 45 degrees. But I'm going to go find out what the tangent on 45 degrees is. Why? Because I can work out where halfway of that interval is. So let's have a look at that, and we're going to say, okay, well, tan of 45 degrees is 1. And that gives us such a nice value. So I know now at 45 and 1, I've got a point over here. Okay, so far we are getting somewhere now, okay, and we're going to get to an exciting point shortly. Now we've got to do the same here. Again, I want the point halfway between 90 and 180, and that is going to be at 135. So now I'm going to go and find tangent of 135, and that gives me a value of -1. So I know I am sitting over here somewhere. Okay, and we would do the same for the next one, which is going to give me a value there. And lastly, if we put halfway through there, it's 315. So let's have a look at the tangent of 315, and we get -1 as well. So we are at this point over here. Now it's a matter of joining the dots. But remember, you can't cross, and this is the shape that you're going to get. And can you see how I'm getting really close, but I'm not going to cross that asymptote? And this gives us a shape that looks like this. This is why I like the tangent function so much, because it's a little bit different and a little spicier. And there we go. There we have our tan function. Now again, in the same way that we've worked with, we now need to have a look at what is going to be my effect on my amplitude and a shift. But for now, we're just going to deal with the amplitude. So let's go and have a look at our tangent function over here. All right, so we have this look, and you can see here would be where we would have our asymptote of 90 degrees and our asymptote of 270. And the question we've just done, we're working from 0 to 360. Remember, that's the domain we deal with, and that takes me to there. Remember, it does continue, however. So let's have a look at our tangent function. All right, and we want to 0,5, 10. Let's see what that is going to have an effect. And can you see how it changes and has it is stretched out a little more? Remember, the smaller the value, the wider the graph is. The bigger the value, the more stretched the graph is. And let's have a look at 2 tan x, where now you're going to expect a more stretch. So can you see this is our original, and it would be a little more stretched. Okay, and that is our effect on our tan. Alrighty. Going back, what about our effect on the shift? So we know that y is equal to a tan x plus q. Our vertical shift refers to the value of q. Add q, you're shifting the function up. Subtract q, you're shifting the function down. Now, if you have a look at what we have just drawn, some of you may be looking and going, all right, but if I shift this up and down, it's not going to change too much, and indeed it doesn't. So let's have a look at what that looks like over here. So if we look at tan and add 1 to it, I want you to visualize what you think this is going to look like first. And there we go. I hope that's what you visualized, that you're actually moving that up. And imagine this without our standard blue. So we can take that out so that you can see. That's what it looks like. I hope that you are certainly feeling a lot more comfortable with your trig functions, and that you've realized that if you know how to do your standard, that the transformations are very, very nice and easy. Bearing in mind the key focus for each function, you must know what the shape looks like, all right? What effects are on the intercepts when we change the amplitude and shift the graph up and down? What are your maximum and minimum values? What is the domain and range of each of your functions? What is an asymptote, for example, okay, and amplitude and period. So if you're feeling a lot more confident with this, it was a fabulous lesson. I thoroughly enjoyed working through this. Hope you did as much. And until we see one another next time, goodbye.